In this lesson, we're going to look at three standard formulae. One is for the sum of the first n natural numbers, one is for the sum of the first n square numbers, and one is for the sum of the first n cube numbers. So the first one is one that we need to learn. The second two are both given in the formula book. So the natural numbers are the positive integers starting at 1. So the rule for that is just r. We are going to just work out some of these summations by writing them out. So the first one is the sum of the natural numbers starting at 1 and ending at 3. So that would just be 1 plus 2 plus 3, which is 6. We can do the same with the sum of the natural numbers from 1 to 5. So 1 plus 2 plus 3 plus 4 plus 5 gives us 15. We can do the same for the sum of the first 8 natural numbers. It gives us 36. Or the first 10. That gives us 55. So we're going to look for a general formula for this. If we wanted to add up the natural numbers starting at 1 and ending at some value n, we're going to look for a formula that will calculate this. So we're going to try and find a formula for the sum of the first n integers. So that is sigma r from r equals 1 up to n. If we wrote that in full, we would get 1 plus 2 plus 3 plus the dot 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 just shows that we are missing a few terms out. And the last few terms are plus n minus 2 plus n minus 1 plus n. So the way that we can think about finding a formula for that is we can write out 2 times that formula to begin with. So 2 times the sum from r equals 1 to n involves writing out the same line twice. So 1 plus 2 plus 3 all the way up to n plus another 1 plus 2 plus 3 up to n. And the reason we're doing that is because we can then write the second line in reverse. So if we reverse the second line, so we start with n and then go down until we get to 1. We've then got 2 lines with the same summation twice but written in different orders. Now here we've got a pair, 1 plus n. We've then got another pair, 2 plus n minus 1, which is also 1 plus n. We've got a third pair, 3 plus n minus 2, which is also 1 plus n. So all the way along, all of these pairs add up to 1 plus n. So we've got n plus 1 plus n plus 1 plus n plus 1. And there are n of those terms, because we had n terms in each original line. So altogether, that summation is n times n plus 1. We can write that as 2 times the summation that we're looking for is n times n plus 1. Because we only want the summation once, we now need to divide it by 2, which leads us to the formula that the sum of the first n positive integers, the first n natural numbers, is a half n plus 1. So that could be used, for example, if we wanted the sum of the first 20 integers, positive integers, we would just substitute 20 in there. We do a half times 20 times 21 to get an answer. Now, this is not given in the formula book. You need to learn this formula. You also need to be able to prove it, so you need to know the proof that we've just gone through there. So there are 2 more formulae that are given in the formula book. The first one is the sum of the first n square numbers. So that is sigma r squared from r equals 1 to n. That would expand as 1 squared plus 2 squared plus 3 squared all the way up to n squared. The formula for that is a sixth n plus 1 to n plus 1. And then the sum of the first n cubed numbers, so 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed, that is given as a quarter n squared n plus 1 squared. Now you don't need to know the proof for these, and these are just given to you in the formula book. You may notice, however, that the formula for the sum of the first n cubed numbers is actually the same as the formula for the first n integers, but everything's squared. So the one for the integers was a half n plus 1, whereas this is a half squared n plus 1 squared. So the proof for that is beyond the scope of the course, but it is interesting to look up if you are interested. So these are the formulas that need learning. So there's the one we've just done for the sum of the first n integers, which is a half n plus 1. The other one is the sum of the number 1. So if the number 1 appears in a summation, then you need to remember that isn't just a single 1, that is actually n ones all added together, 1 for each time it appears in the summation. So the sum of 1 from r equals 1 to n is n. And similarly, if you had a different number here to 1, say if you had the sum of 5 from r equals 1 to n, the answer would become 5n, because it would just be n fives. So we're going to look at how the summations that we've just looked at on the previous slide can be used to find related summations. So first of all, we're going to start with the sum of 4r from r equals 1 to 5. So we could write that out using the rule. So we could say if we substituted in 1, 2, 3, 4 and 5 into the rule 4r, we would get 4 plus 8 plus 12 plus 16 plus 20. Because they're on the 4 times table, we could factorise out the 4, giving us 4 times 1 plus 2 plus 3 plus 4 plus 5. And obviously in the bracket, that 1 plus 2 plus 3 plus 4 plus 5, that is just the sum of the first 5 integers. So we could write that as 4 times the sum of r from r equals 1 to 5. So from that we can see that if we had a question like this, we could factorise out the 4, bring it to the front here, and then use the rule that we know for r. So this, we would use the half n plus 1 formula to work out the rest of this. So for the second question, I'm going to look at what happens if you've got a sum here. If the rule was r plus r squared, if we were going to use r equals 1 to 3, we could put in 1, that would give us 1 plus 1. We could then put in 2, which would give us 2 plus 4, then put in 3, which would give us 3 plus 9. But by rearranging those terms, putting together the first terms and then putting together the second terms, we can see we've just got 1 plus 2 plus 3 and then 1 plus 4 plus 9. So that is actually just the sum of r from r equals 1 to 3 plus the sum of r squared from r equals 1 to 3. So if you've got something like this where you've got two parts to the rule, you can split it into 2 separate sums and use each of those formulas separately. So this one would use the half n plus 1 rule. This one would use the 6th n plus 1 to n plus 1 rule. And then finally, we've got the sum of r plus 3, starting with r equals 1 going up to 4. So again, if we write that out in full, we would get 1 plus 3, and then 2 plus 3, and then 3 plus 3, and then 4 plus 3. So just rewriting that in a different order, we could write 1 plus 2 plus 3 plus 4, so the first term in each of the brackets together. And then the 3's, if we put those all together, you can see that we've got 4 3's at the end as well. So we can think of that as being 1 plus 2 plus 3 plus 4, which is the sum of the first 4 integers, plus 3 lots of 1 plus 1 plus 1 plus 1. So what that is the sum of the first 4 integers, which would use the rule half n plus 1. And then this 3 here is actually 3 times the sum of 1. So in general, if there was an n at the top here rather than a 4, this term would become 3n. Okay, so we're going to use the rules on the previous slide to find the sum of the series that's formed using the rule 3r minus 4. But instead of starting at r equals 1, we're going to start at r equals 60 and go up to r equals 80. So we could do this the long way. We could start by substituting in r equals 60 as our first term, 3 times 60 minus 4, then do 3 times 61 minus 4, 3 times 62 minus 4, and keep going all the way up to 80, 3 times 80 minus 4. Add up all of those terms and we will get the answer. However, we're looking for a quicker way. So first thing we're going to do is split up that summation using the rules that we have just seen. So the sigma of 3r, the sum of 3r, we could write that as 3 times the sum of r. Still starting at r equals 60, going up to r equals 80. And the minus 4, we're going to write that as minus 4 times the sum of 1, starting with r equals 60, finishing at 80. So we now need to deal with the fact that those sums start at 60 rather than 1. What we can do, is, because the formula that we've got, the formulas start with 1, we could do the sum starting from 1 going up to 80, so that will give us the sum of the first 80 terms of each series. And then we could say, because we want to start at 60, we don't actually want the first 59 of those terms. So we're then going to take away the sum starting from 1 ending at 59, and that will leave us with the 60th term up to the 80th term. So essentially what we're doing, if I use the letter S to represent sum here, I'm going to do the sum S80, which is the sum of the first 80 terms, take away S59, the first 59 terms. I'll do the same for both of those. So the first term, this 3 times the sum of the integers, if we work out 3 times the sum of the integers starting at 1 ending at 80, if we then take away 3 times the sum of the integers, starting at 1 and ending at 59. So this is the first 80 terms. The first bit is the first 80 terms added up, but then we're taking away the first 59 terms, and that will leave us just with the terms starting at 60, ending at 80. Notice that 59 is one less than 60, so be careful with the number that you use for the second one there. Right, and then for the second part, we just need to be careful with this minus as well. So I've got minus. I'm actually just going to use some brackets to make sure that we don't get messed up with the negatives there. So the first part is going to be 4 times the sum of 1, starting at r equals 1 and going up to 80. Then I'm going to take away 4 times the sum of 1, starting at 1, ending at 59. So that's going to do the same job again. It's going to work out the sum from 1 to 80, and then we're going to take away the sum from 1 to 59, leaving us with the sum from 60 up to 80. So those brackets were important just so that we didn't get any negative errors there. Okay, so we've now got 3 times the sum from r equals 1 to 80 of r, which we'll use a formula for, minus 3 times the sum from r equals 1 to 59 of r, minus the sum, 4 times the sum of 1 from r equals 1 to 80. Then minus minus is going to give us a plus on the end, so plus 4 times the sum of 1, starting at r equals 1, ending at 59. So the first two we're going to use formulas. So we're going to use, for the first two, we're going to use the half n plus 1 formula. But that is the sum from 1 to n of r. That becomes a half n plus 1. So that's what we're going to use here. So this one, the 3 at the front is just going to stay as it is. And the sum from r equals 1 to 80 is going to be a half times n is 80, so that's 80 there, times 80 plus 1, so that's 81. That is the first term. Then got minus 3 times, and I'm going to do the same sum again, but this time it's the sum from 1 to 59, so n equals 59 this time. So it's a half, 59, and then n plus 1 becomes 60. Now the last two are much simpler. Remember that the sum of 1, what that's saying is that you've got however many terms there are, n, so in this case 80, that's how many ones there are. So sigma 1 from r equals 1 to 80 is just going to be 80n. So we've got minus 4 times 80. And finally here we've got plus 4 times 59. Okay, so working that out, we get 9,720 minus 5,310 minus 320 plus 236. So altogether, that summation, we get 4,326. Okay, so I mentioned before that there is a summation button on the calculator. It's just underneath the on button where the X is. If you look in yellow at the top, there's a summation there. If you press shift and then press that, you will get the summation. You're going to need to write the rule in terms of X there. So you're going to use that same X button. You're going to write the rule out, 3r minus 4, so 3x minus 4 in this case. You can then just scroll along. You can put the bottom value in as 60, the top value in as 80. And the answer will come out as 4326. So you can check these on the calculator. However, the calculator is not a substitute for being able to do this fully, because sometimes you may be asked to show you working out, and sometimes you may be asked to do this in terms of n, in which case you would need to do it without a calculator. So here are 3 more summations similar to the one we've just done. I'd like to pause here and have a go at working out each of those 3 and then turn over to see the answers on the next slide. Okay, so the answers are given on there. So sometimes these summations are given in terms of n rather than in terms of a particular number. So this time we're going to look at the summation of the rule r plus 1, r plus 2, starting from r equals 1 and going up to n. We've been told that the answer is in the form of third n and then n squared plus pn plus q. P and q are integers that we need to find. So in order to do this, we're going to start with the left-hand side, which is the sum of r plus 1, r plus 2 from r equals 1 up to n. I'm going to need to expand those two brackets. So if we expand those, we get the sum of r squared plus 3r plus 2. Now that it's been expanded, we can then write that as three separate summations. So we can call that the sum of r squared plus 3 times the sum of r plus 2 times the sum of 1. And we can now use the formulas to write down those. So the formula, remember the formula for the sum of r squared is in the formula book, a sixth n, n plus 1, 2n plus 1. The other two you need to know, so you need to know the sum of r is half n, n plus 1. And the sum of 1 is just going to be n, because that's just n ones added together. So substituting those in, don't multiply these out because we're going to see if we can factorise anything. So the first term becomes a sixth n, n plus 1, 2n plus 1. That's just using the formula. The second term becomes 3 times and then a half n, n plus 1. Again, that's the formula. And the third term just becomes 2n. So we're not going to expand that. We're going to look and see if we can see any common factors. We can see that n is a common factor. We can also see that a sixth is a common factor. When I say it's a common factor, we can obviously pull a sixth out of the first term. But what we are really doing when we are factorising out a sixth is we are dividing by a sixth. And remember that dividing by a sixth is the same thing as multiplying by 6. So what you can actually do, if you were going to pull a sixth out to the front, you could multiply each of these three terms by 6, and that is what will be left inside the bracket. So by doing that, we're going to end up with a sixth n at the front, and then everything else expands here. So we've still got n plus 1 times 2n plus 1 here for the first term. The second term, the 3 over 2 has been multiplied by 6 to give us 9. And finally, the 2 here multiplied it by 6 to give us 12. So just expanding out those brackets gives us this. That will simplify down to give us a final answer of a sixth n and then 2n squared plus 12n plus 22. So you can see the value of P is 12, the value of Q is 22. So in this question, we're being asked to show that the sum of r squared minus r from r equals 1 up to n can be written in this form here. We are told that k is a rational number, that means it can be written as a fraction, and we're told that a and b are integers, so whole numbers. So again, we're going to start with the left-hand side, and we're going to write that out as two separate sums. So the right-hand side, r equals 1 to n, the sum is going to become r squared minus, and then the sum from r equals 1 to n of r. So we've got two separate sums. Both of these use the formulas. So the first one, the sum of r squared, is a sixth n, n plus 1, 2n plus 1, minus, and the second one is a half n, n plus 1. So it's really important here that you don't try to multiply out these brackets, because we're going to look and see if there's any common factors that we can pull out instead. So immediately, I'm just looking at the letters here, I can see that there's a common factor of n in both terms, and there's also a common factor of n plus 1 in both. So I'm going to pull out both of those things. So n plus 1. Okay, so what's left if I pull out n plus 1? The first term, there's still a sixth there, and there is still a 2n plus 1 there. Minus, I've still got a half here, and I've got, that's it, just a half, because the n and the n plus 1 have both been factorised out. Okay, so I'm aware that I need integers inside those square brackets, because the question says that a and b are integers. So I'm going to look at a sixth and a half and look at which fraction would be the best one to pull out there. I'm going to pull out a sixth from both. So if I factor out a sixth, I'm going to get sixth n plus 1. And then What we're doing to everything inside the bracket is we are dividing it by a sixth, which is why the sixth is coming outside. So dividing by a sixth is the same thing as multiplying by 6. So the first bracket, if you multiply that by 6, is just left as 2n plus 1. The half, if you multiply half by 6, you get 3. That becomes minus 3. So we're almost finished. We've got a sixth n plus 1. Then here we've got 2n, and then 1 minus 3 is minus 2. So we're almost done. But then when we look at the original question, we see that both the brackets start with just n, whereas we've got a bracket that starts with 2n. So what we're going to do to rectify that is we're going to pull out a factor of 2 from our second bracket, and we're going to put that with the sixth. So we're going to make it 2 sixths, or 1/3. That becomes 2 sixths n plus 1. The second bracket is now n minus 1. 2 sixths simplifies down to 1/3. So we are left with 1/3 n plus 1 n minus 1. So we can see that k is 1/3, a is 1, and b is minus 1. So this question comes in 2 parts. The first part asks us to show that the summation at the top can be written as it says. And then the second part asks us to use that rule to help us find the sum of the squares of the odd numbers between 100 and 200. So we'll start with the first part. I'm going to show, so we're working out the sum from r equals 1 to n of, I'm just going to expand out that bracket. So I've got 2r minus 1 all squared. That expands to give us 4r squared minus 4r plus 1. So that can be split up into 3 separate sums. So that can be split up into 4 times the sum of r squared, from r equals 1 to n, minus 4 times the sum of r, from r equals 1 to n, plus, remember that this isn't just a 1, this is the sum of 1. The sum of 1 from r equals 1 to n. So that is a 1 n times. So that answer is going to be n at the end, 1 times n. Okay, so using the formula for the first two, I've got 4 times, then the formula for r squared is a sixth n plus 1 to n plus 1. I've then got minus 4 times the formula for r, which is a half n plus 1. And the third one, it's a common mistake here to put 1, just remember that it's n, because it's the sum of n ones added together. Right, now do not expand this out. You need to just look and see if there's anything that can be factorised out first. I can see that an n can be factorised out. So n times, let's see what else there is. Okay, 4 times a sixth, that will simplify down to 4 sixths or 2/3. And then what's left here is n plus 1 to n plus 1. I've then got minus 4 times a half is 2. The n has been factorised out, so that is n plus 1. Then finally, the third one, it's just n. Because the n has been factorised out, that is going to be plus 1. So there's now nothing else that we can factorise out there. Although there is a factor of n plus 1 in the first 2 terms, there isn't a factor in the third term. So there's nothing else can be factorised out. So at this point, we are going to then need to just multiply everything else out inside the bracket. Actually, before I do, just notice that we need to pull a third out. I'm going to pull a factor of a third out at this point, just to make the numbers a little bit easier. So if we pull out a factor of a third at the front, remember that by factorising out a third, what we're really doing is dividing everything else by a third, which is the same thing as multiplying by 3. So we're going to multiply everything inside that bracket by 3. 2/3 becomes 2. So 2n plus 1 to n plus 1. The next one, I've got 2n plus 1. Well, 2 times 3 is 6. That's going to become 6n plus 1. And then finally, that 1 needs multiplying by 3 as well. So that was from factorising out the third. So we've got a third n. And then what is left, just being careful to expand this, I've got 2 times, that is going to become 2n squared plus 3n plus 1. Then got minus 6n minus 6 plus 3. So that becomes a third n. Okay, so we've got 4n squared here. We've then got plus 6n plus 2 minus 6n minus 6 plus 3. So the final answer, get a third n, and that all simplifies down. We've got 4n squared. The 6n and the minus 6n cancel out, and we've then got minus 6 plus 2 plus 3 is minus 1. So that gives us the final answer there of 4n squared minus 1. So for the second part of the question, the word hence means use what you've just done. So we're going to somehow use this formula to find the sum of the squares of the odd numbers between 100 and 200. So what this is asking is it's asking us to take the odd numbers between 100 and 200. So start with 101, square it, then 103, square it, 105, square it, and keep going until you get to the last odd number before 200, which is 199, and square that. So we need to be able to use the formula that we've just acquired. We can see 2r minus 1 is a general way of writing an odd number, because if r is an integer, 2r will always be an even integer. So if you do 2r minus 1, you will always get an odd integer. So if we can work out where to start and where to stop with this formula in terms of r, we should then be able to work out the answers over there. So starting here, if we want 2r minus 1 to be the first number, 101, that means that 2r is 102, so r is 51. So that's telling us that if we start with r equals 51, then the first term will be 101 squared. Let's just work out where we need to end. So we need 2r minus 1 to equal 199. That means that 2r equals 200. So r is going to equal 100. Okay, so in order to get the sum that we need, 101 squared plus 103 squared all the way up to 199 squared, we should be able to do that using this formula, 2r minus 1 squared. If we start with r equals 51, we'll then get to stop when we get to r equals 100. Okay. So in order to do that, we're going to need to do two separate sums. We're going to need to do this first of all, the sum from r equals 1 to 100 of that rule, 2r minus 1. And then we're going to take away the first 50 terms, so that we only start at r equals 51. So we're then going to do the sum from r equals 1 to 50, of, I missed a squared off there, 2r minus 1 squared. So we just need to first of all substitute 100 into the right hand side, and that will give us the first term. Then it's to say minus and then substitute 50 in to get the second term. So here this is going to be a third times 100 times 4 times 100 squared minus 1. Then minus, and then we're going to do the same thing but for 50. So this time we've got a third times 50, then got 4 times 50 squared minus 1. So if we calculate both of those, that should give us the answer that we're looking for. So that first term is a big number. We've got 1, 3, 3, 3, 3, 0, 0. So that's 1,333,300. Minus, if we do the same for the second one, we get 166,650, giving us a total sum of 1,166,650. In this example, we want to find the sum of a series starting with the n plus 1th term and going up to the 2nth term. So where we're going to tackle that is we're going to find, first of all, the sum of the first 2n terms, so from r equals 1 to 2n, and we're then going to subtract the terms that we don't want. So we don't want the first, second, third, all the way up to the nth term. So we're going to take away the sum from r equals 1 up to n of 6r squared. So So if we calculate those two things separately, we can then find the difference, and that will be the answer. I'm going to start with the sum from r equals 1 to n of 6r squared, because that one's slightly easier to do. So I'm going to pull the 6 out to the front. 6 times the sum r equals 1 to n of r squared, and the formula for that is 6 times a sixth n plus 1 to n plus 1. That's going to work out as n plus 1 to n plus 1. Then we use that to find the sum of the terms from 1 to 2n, 6r squared. So we can actually just use the formula that we already found in the first part and just replace all the n's with 2n. So if we replace all the n's with 2n from the previous line, we're going to get 2n plus 1, and then 2 times 2n is 4n, so 4n plus 1. So to find the sum that we are looking for, the sum from n plus 1 to 2n, we're just going to find the difference between those two terms. So it's going to be 2n and then 2n plus 1, 4n plus 1. That's the sum from r equals 1 to n, minus n plus 1 to n plus 1. So before we multiply any of this out, we're going to look and see if we can find any common factors to pull out. I can see that there's a common factor of n in both terms. There's also a common factor of 2n plus 1. So I'm going to pull that bracket out as well. That leaves us with 2 and 4n plus 1 from the first expression, minus an n plus 1 from the second expression. So that will simplify down to give us n, 2n plus 1. We've then got 8n plus 2 minus n minus 1. So the simplified answer is n, 2n plus 1. Then got 8n take away n is 7n, 2 take away 1 is 1. So the sum we're looking for is n, 2n plus 1, 7n plus 1. Now please complete exercise 11b on page 241.